Welcome to our webinar, Educational Interactive Flow Visualization Analysis Systems. This is Sanchez from TESCON India. For over 25 years, TESCON has been providing advanced flow measurement techniques such as PIV, LDV, and high-speed imaging systems for research and development in fluid mechanics. In addition to these research-grade instruments, we offer educational interactive flow visualization and analysis systems for science and engineering education. Our presenter today is Dr. Murad Oke from our principal company, Interactive Flow Studies USA. Dr. Murat will provide an insight into the very versatile visual and analytical tools specifically developed for educational purpose for a variety of fluid mechanics phenomena. If you have any questions during the presentation, please type them into the chat box in your control panel. We'll answer the questions after the presentation. Welcome, Dr. Murat.
Hello, my name is Murat Okçay, and I'm the co-founder of Interactive Flow Studies. Thank you for joining us. Now, our mission is to develop innovative, state-of-the-art systems for teaching and basic research in several subjects, including hemodynamics, fluid mechanics, heat transfer, design and manufacturing at schools worldwide, which enables deeper learning through hands-on experimentation, hence the name Interactive. Now, we're a US company based in the US. Our customers are worldwide, including the Americas, the Middle East, Europe, and Asia. Here are some of the customers I managed to fit in one page. As you can see, there are quite a few in India. Now, a little bit of background. Why did we get into this business in the first place? I'm a mechanical engineer by training. I'm actually a professor as well. I teach fluid mechanics, heat transfer, and all my life, my background was fluid mechanics, but it's a difficult subject to learn, and we all have to admit that. The equations are very complicated for students. We're talking about Navier-Stokes equations and so on. So there must be a way to teach students this difficult subject. And yet, fluid mechanics is a highly visual subject. Having spent many years in industry, we felt that there are technologies that industry uses all the time that we can bring to students. But unfortunately, the equipment industry uses are very expensive, prohibitively expensive, and dangerous, high power lasers and so on. So we were the first company in the world to develop and commercialize an educational version of these systems. Now, going back to fluid mechanics, like I said, it's a highly visual subject, as you can see, and it's in everyday life, ranging from designing drones. Fluid mechanics is a very important field that we have to understand. Heart valves, designing heart valves, looking at bird flight so we can design better airplanes, controlling pollution, looking at airflow around buildings, and more recently, how coronavirus is spreading. So, in a nutshell, fluid mechanics is very important, and it's highly visual. So one way to take advantage of this is to utilize some tools, theoretical and experimental. Now, theoretical tool that we have is called a computational fluid dynamics. Those of you who don't know what that is, it's short for CFD, and it's a theoretical tool, analytical tool. Basically, you divide the flow field into grids and then perform numerical analysis using very powerful computers. And as you can see, they can generate highly visual and educational, instructive visual images. But this is all theoretical. So CFD is just theoretical, not experimental. There is a similar technology that produces just as pretty pictures and educational pictures, and it's called PIV. Now that's called particle image velocimetry. The reason why it's called particle image velocimetry is because We seed the flow with particles ranging from 10 microns to 50 microns. Basically, it's called seeding the flow. And these particles are illuminated using light in the form of LED or laser. And a digital camera is synchronized with the illumination. So it captures images, sharp images. So you can see those particles on the right-hand side moving there for you. And those are multiple images taken consecutively and analyzed. And basically, the distance the particles move, knowing the delta t between the two images, will give you the velocity field. Speed is distance over time. So using cross-correlation techniques, we can determine the global velocity field. And here's a real-world PIV analysis over a racing car. Now, there are a variety of fluid mechanics phenomena that involve fluid-solid interactions that can be studied with our systems. Some of these fundamental topics include shear, vorticity, passing flow, potential flows, two-phase flows, bubbles in liquid, for example, boundary layers, flow past the body, fully developed flows, conservation of mass. Our systems also teach how to use particle image velocimetry. We'll be studying laminar and turbulent flows, visualizing streamlines, straight lines, path lines. Also, outside fluid mechanics, we can also study heat transfer and many other phenomena. So what we've done is we integrated the state-of-the-art technologies such as particle image velocimetry, laser Doppler velocimetry, that's two beams intersecting. We can go into details if you wish later. Fluorothermal camera, CFD, and computer-aided design into interactive educational experimental systems that are versatile and affordable, designed to enable students acquire 21st century knowledge and skills. This is what industry uses, and the sooner the students are exposed to this, the better. So I'll be going into details of each product that we have developed over the years, and where they can be used and how they can be used and what kind of results you can achieve. So we have designed, these are the systems that we've designed. They're called HemoFlow, Flow Coach, ePIV, ThermoFlow, and MiniPIV. And FlowX is the software that's common to all of them. But before we start talking about the products, let me just quickly tell you where they can be used. HemoFlow is specifically designed for biomedical engineering, but of course anybody who studies fluid mechanics can also use that. Because all our flow models are interchangeable, manufacturing comes into play. So students can learn how to manufacture molding, machining, rapid prototyping. They learn all that too. ThermoFlow is teaching heat transfer, fluid mechanics. Flow Coach is teaching fluid mechanics. So is ePIV. Now, MiniPIV is the measurement technology. The HemoFlow, ThermoFlow, Flow Coach, and ePIV are experiments utilizing PIV. Okay, so let's start with FlowX software. There is actually a demo online, but there is an outage in the Bay Area in California, where the server is. So I think it should be back by tomorrow. Please feel free to go online and see FlowX software in operation. Now, some of the features include integrated PIV and CFD analysis. So we have PIV and CFD integrated so that students can perform experiments and then compare it to their theoretical results. It has integrated CAD, a basic CAD system where you can model, create models for CFD, or even for manufacturing the inserts, interactive flow model inserts. One feature, important feature, is web-based. So I'm going to explain a little bit more about that later. It displays and captures flow video and images. It exports images, data, or results for further analysis if required. It's fully interactive. No setup is required. Remote control of digital USB 2 or Ethernet camera. Works with all PCs, including Apple computers. And it is written like a book, so it's full of flow theory explanations as well. And linked to web-based, it's multiple PC capable for team study. Now here are some specifications. As I mentioned before, there is a demo online. One important point I like to make is the software is open source, so we allow the user full access to the code. For example, it has interrogation and data validation features, but those are simplified for educational purpose. But if the student or professor would like to learn more or explore more, they have full access and utilize further capability of the software. The PIV is GPIV. That's what we use. And post-processing, the software has its own post-processing. It's quite capable of producing graphs and, as you can see, images, videos, and so on. But if the student would like to explore the data further, analyze data further, he can export the raw data for further analysis, like using Techplot or Excel. Well, here's a snapshot of the software. It has many pages, so if you follow my arrow, mouse key, on the left-hand side, the student starts with quick start and sets it up and acquires the image and then analyzes and then performs CFD and then stores it in a session which can be exported. The output data is stored here. This section has flow theory, and it has links to useful websites and so on. Going back to the web page, web-based feature. Now, on the left-hand side, I put ideal for corona distance learning. It is true. A lot of universities in the US, and I'm sure over there too, is affected by coronavirus, and group effort is becoming more limited. But our feature, the web-based feature, is great because the system can be located in a lab with one person operating it, a professor or a teaching assistant. And if it's connected to the internet, or even the intranet, the students can access the equipment remotely, perform experiments, collect data, analyze, and everybody will perform analysis differently because there are different options and so on, and then send in their results. So they don't have to work as a team, or they can work in groups of 3 or 2, but it's ideal for corona distance learning. Now, we have next mini PIV. Now, mini PIV is a measuring instrument. It is not an experiment. It's an instrument that is basically a PIV system. And it's called a mini PIV because it's got limited power and resolution. So it's a standalone PIV measurement. It's very easy to use and set up. It's precise synchronization of the camera and pulsing light source. Accepts CS or C-mount lenses for the camera. It has a high-performance 1,000 milliwatt laser diode inside a robust case. It's quiet. It doesn't require external cooling because it's got an integrated active cooling system. It has an outstanding laser sheet, less than a millimeter thick. It has also an optional waterproof 200 milliwatt laser, if required. This is an optional LED version that connects to flow coach for further enhancing the PIV capability. And there is another option, yet another option. There's a standalone mini PIV suite with a 32-watt white light LED arrays. And that's volume illumination. Of course, the most capability is obtained with the 4MP camera, that's 4 megapixel camera, and a 1,000 milliwatt laser. Here are some of the features. Like I said, the lasers do not require cooling. They're solid state, very stable. And here are some of the features. We also actually have 1 megapixel camera too. Now the EPIV system was the first system we designed a long time ago. It was meant for desktop. As you can see, there's a picture of a user there that shows you the scale. It is compact and portable. It's only 15 by 11 by 7 inches. By the way, all our systems comes with FlowX software. The limitation with this system is the flow is only laminar. Now you can instantly change the flow direction, visualize flow streamlines at various flow speeds and directions, quite capable for its size. Ability to vary flow speed dynamically, studying flow speed effect on flow phenomena. Fluid mechanics principles can be studied with different flow model inserts. As you can see on the left, you can have different shapes inserted into this flow model, which is inserted into the flow experiment. The system comes with 6 flow model inserts, but students can design as many inserts as they like. Users can design custom flow models inserts using the CAD system or SolidWorks or any other CAD system that you have. Global flow field measurements with particle image velocimetry, it is built in. Ability to increase the PIV seeding density on the fly. You can add more dense seeding if you like. That actually teaches students how to use PIV, because the density, seed density, is a very important factor in the use of PIV. It's very safe and robust. Everything is enclosed with a water-cooled laser. Reynolds number under 100 based on water flow through a 25 by 5 millimeter flow model insert channel. And like I said before, it has an integrated camera and laser inside. It's very interactive and visual, and it's very easy to set up. And here are some of the images you get with this system. As you can see, this is an instantaneous flow direction. The student can change the direction of the flow at will, and the speed. So as you can see the vortices and flow paths. Like I said, for its size, it's quite capable. And here is another one. I think this one has music, so. As you can see, it's quite capable. Now, next came FlowCoach. FlowCoach is a more advanced version of EPIV, effectively. It's still an educational system and basic research. The components involve a flow meter, mechanical flow meter. It has LED illumination, a pulsing LED, PIV camera. Like all the systems, it has interchangeable flow model inserts, and it has a self-contained water reservoir. And they all have a handle. I'm not sure if you noticed that, but they all have a handle right there. So it's portable. Now, it comes with FlowX software. The advantage of the system is the flow can be analyzed, in laminar flow, transition, and turbulent flow visualizations is possible. We can measure the flow rate and pressure measurements. Fluid mechanics principles can be studied with different flow model inserts, like all our systems. It has interchangeable flow model inserts. User can design custom flow model inserts. It's portable. You can take it into any classroom and connect it to a projector, and you can project the results on the screen if you like, or leave it in a lab. It has the ability to vary the flow speed dynamically, studying the speed effect on the flow phenomena. You can obtain the global flow field velocity measurements with particle image velocimetry. You can add seeding for flow visualization and particle image velocimetry. Now it's interesting that the seeding is specifically for particle image velocimetry, but it can also be used just for flow visualization. You can just actually see the flow because it's got a transparent window. Ability to increase the PIV seating density on the fly is a feature. Now, this feature is unique. I'm still not able to explain how it works, but we have a foamy solution we add to the liquid, to the water, and you can change it back and forth between foamy liquid and clear water dynamically during an experiment. When it's foamy, you can actually see the vortexes really clearly. And just by switching something, I can show you there, but this thing here, it becomes clear again. So it's a great feature. It's a mystery how it works to me. But then again, I'm only the co-founder. Add or remove air bubbles dynamically during experiment for great visualization and analysis. Reynolds number for the Venturi insert is 25,000 at 5mm by 5mm at the narrowest cross section. I believe that's the Venturi. And Reynolds number is 3,000 at 80 by 5mm cross section based on water with valve fully open. You can measure the differential pressure for the Venturi insert is about 1 psi. Now it has the self-cleaning feature, so you don't have to open the model to clean the surface of the screen there. It self-cleans. Integrated digital camera for real-time laminar and turbulent flow visualization and laminar and turbulent PIV analysis. Software can support multiple video formats, which means the user can use their only digital camera for flow visualization and analysis. It's interactive and highly visual. It's very easy to set up. And one more feature is you can actually add a mini LDV system to it too, to make it even more accurate. Now here are some of the results that we have from FlowCoach. The insert is 80mm by 80mm. This one is anodized aluminum. It's 40mm high. I'm going to click this, and this is the kind of flow visualization you can actually get with the system. Obviously, this is not meant for PIV. It's meant for flow visualization, and you can change the exposure of the camera to achieve images like this, videos like this. You can clearly see the rotational flow behind the obstruction, square obstruction there. And the user is changing the speed to see the effect. Now for PIV, you would want very sharp images of the seed particles, as you can see on the bottom left corner there. And that's you can achieve that by, again, adjusting the camera controls using FlowX software. If you look carefully, you can actually see the red vectors, velocity vectors, superimposed on the spots. Now the flow is slowing down. You can actually clearly see the vortex, beautiful vortex behind the square there. Now it's going to speed up, accelerate. You can actually see the stagnation point and so on. That's the self-cleaning feature that cleaned up the surface there. And the middle one, again, if you control the exposure and so on, you can get all kinds of images. And this one, I think, is an average of all the images. The bottom right-hand corner is the PIV experimental results, actual velocity vectors and shaded diagram. The shade, I think blue is slow and red is fast. All kinds of flow model inserts can be made. The ones on the left are orifice, nozzle, and Venturi. The one here is a Venturi with 2 pressure taps. It can measure pressure differential. And this one here is an airfoil. This comes with the system as well, actually. It is adjustable, so you can measure look at the flow at different angles. Here's some examples. This one is interesting because this was purchased by a biomedical engineering department. So this system can be used by biomedical engineers. Here's a model, a 2D model of an aneurysm. As you can see, the recirculation of the aneurysm, that's what makes the aneurysm get bigger, I believe. Okay, so what we've done in the past is we've taken these systems to high schools and asked students who have very little knowledge of fluid mechanics to come up with some shapes and sketch the flow lines around these objects that they picked. And then we went back and then built these little models and inserted them into FlowCoach. and went back to the school and showed them and compared their predictions to actual data. And here are some of the images they came up with. The one I like is the starfighter from Star Wars. Here's a chair, there's a shark fin, and so on. Next comes thermal flow. Now, thermal flow is like flow coach, but it has enhanced features such as digital measurements and floor thermal camera and heated inserts. So like all our systems, it comes with FlowX software, because FlowX software has built-in capability for performing thermal analysis, PIV, CFD, CAD. It's all built in. This one, thermal flow, has heat transfer. It can perform laminar transition turbulent flow visualization. Temperature, flow rate, and pressure measurements are measured with digital user-friendly multi-channel display controllers and data acquisition system. Heat transfer and fluid mechanics principles can be studied with different interchangeable heated flow model inserts, and user can design custom flow model inserts. The FLIR thermal camera imaging provides dynamic live global temperature visualization of the flow and flow model inserts. So you can actually perform PIV analysis and thermal analysis at the same time. Global flow field measurements with PIV system. Integrated LED-based mini PIV system with digital camera for PIV flow visualization and analysis. It's portable. It's got on a handle. Take it into any classroom. Ability to vary flow speed dynamically, studying flow speed effect on heat transfer and fluid flow phenomena. So you can change the speed and see how the cooling effect is. This bottom section here is where the reservoir is. So you don't have to connect this to any water. It has its own reservoir. It's recirculating reservoir. It has the ability to increase the PIV seeding density on the fly. You can have water or airflow or a combination of both. Add or remove air bubbles dynamically during the experiment for great visualization analysis. It has the self-cleaning feature as before. Software, again, can support multiple video formats. It's very quiet. Automatic control of the heater with built-in temperature limits and safety features. So you set the temperature and it will control it to that temperature. Interactive and highly visual. It's easy to set up. And just like the previous systems, an optional mini LDV system can be added on to. Here is an experiment, transient experiment. Flow is off and heater is turned on first. Once the surface temperature is around 50 degrees, flow is slowly turned on and FLIR camera captures the video to see what happens. And later on, we also perform a PIV analysis on this too. So as you can see, flow is slowly turned on. On the bottom left-hand corner is the initial temperature profile, and this is the final temperature profile. And this is the transient temperature profile. Now, like I said, you can perform PIV analysis too, and the bottom right-hand corner shows you the PIV analysis of this section here. And you can superimpose it using graphical techniques. Finally, the HEMOFlow system. The HEMOFlow system is the most sophisticated system we have. It has pulsing flow to simulate heart flow. It's designed for biomedical engineers specifically. It has interchangeable blood model phantoms. Compares, for example, normal vessel to stenosed vessel. Interchangeable real heart valves. It comes with clinically used non-sterile mechanical heart valve. You can vary the pulse rate from 60 beats per minute to 100 beats per minute using FlowX software. User can design custom blood model phantoms. You can actually use blood mimicking fluid as well. I believe you add like 15% glycerin to water. Interactive and highly visual. You can see circulation zones, stagnation zones, separation points. See and quantify changes in velocity vector magnitudes. Utilize velocity profile data to quantify shear stresses. See effects of constriction on inlet and outlet pressures. Control the flow rate. Have steady and unsteady flow rates with associated ability to vary the unsteady pulse rates. It comes with FlowX, of course. It's digital flow rates and pressure measurements. It has integrated LED and laser-based mini PIV system combined actually with digital camera for PIV flow visualization analysis. This is also portable. You can take it into the classroom. Easy to set up, easy to use. Optional optical shear stress sensor to measure wall shear stress. An optional mini LDV system also to add on. The system, a quick description of what the system looks like. If you follow my mouse, at the top there is the flow rate control. Below that is the section where we have the blood vessels, stenosed blood vessels. And these are optically clear, SileGuard, flexible blood vessels. These are actually based on MRI models of real blood vessels. This is the digital flow rate and pressure measurement section. And then we have the heart chamber for interchangeable heart valves. You can perform tests on all kinds of heart valves to see what the fluid is like. And LED for illumination, and also laser is used also. And of course, we have the digital PIV system. Here is one of some of the results here. It's a heart valve. As you can see, the valve is opening and closing, and these are instantaneous velocities. And then you can actually see the particles moving around. These are some of the vectors, instantaneous velocity vectors. And then what you do is you capture those, 100 of these, and then you average them. And then you can get an average velocity field inside the heart chamber. This one is interesting because this is done at ASU. This is like a custom flow model designed by the user. If I started trying to insert a stent into the aneurysm, and so the students, biomedical engineering students, can actually practice putting that in there. It's not an easy task, it's tricky, but once you have the technique down, I guess it's pretty easy. So again, this is not just studying fluid flow, but also practical hands-on experimentation. So that's the stent that is placed inside the aneurysm. Now what they've done is they performed PIV. They actually published a paper on this. The bottom two images are actually from the paper, which is on our website. And then it tells you before and after velocity fields. So apart from learning, the basics of fluid mechanics, heat transfer, etc., flow model inserts can be made by students as an integrated part of the design, build, test, analyze education process, because this is the design cycle that all engineers in engineering use. When I used to design jet fighters in industry, this is what we did. We designed, we built, we tested it, analyzed, and went back to the drawing board, and the cycle went on. And this could be utilized greatly in labs and could be a capstone project. So the students would design a model, build it using rapid prototyping or machining or molding, and then test with some of our systems and obtain graphically stunning educational, interactive educational results, and then compare it to the original design and improve it, and so on. So this is a very important design cycle process. Now, the one on the left shows you what a classroom would look like if you bought quite a few of these systems, for example. It could be in circle desks or on tables or in a lab, as you can see on the right-hand side. This is the courtesy of King Saud University. This is our system being installed. The training will be given by TESCON, of course, in India, and the system will be fully functional and operational, and the users will know how to use them. Like I told you earlier, we took the system to high school students, and they were very interested in this. They love hands-on interaction. All students love that. They were very happy to get involved and play with the system. And I'm sure they learned a great deal. In fact, here are some of the things they said. I'm just going to quote, read one or two. Um, I really liked how we were able to make actual models of the velocity profiles of the fluid flow through an aneurysm and visualizing what actually takes place inside the aneurysm. Another one is it was nice to see how all the different settings in FlowX software affected the picture. It definitely gave us a good idea how liquid flows around the material. So these are not my words. All the students love them. Here is an interview with one of the professors. We asked questions and he answered them, kindly answered them for us.
My name is Dave Frakes, and I'm an assistant professor at the School of Biological and Health Systems Engineering, and also the School of Electrical, Computer, and Energy Engineering at Arizona State University. I'm the PI of the Image Processing Applications Laboratory here at ASU, and we use the Flow Coach and HemoFlow systems both in our research program and also in curriculum that are developed and delivered here in the undergraduate design facility at ASU. So we purchased HemoFlow and Flow Coach to interface directly with our undergraduate bioengineering curriculum where we focus on medical device design and testing. We've been using HemoFlow and Flow Coach for nearly 3 years now, primarily in education, but also in several phases of research here at ASU. We've incorporated the Flow Coach and HemoFlow systems into our curriculum in several ways. Most notably, we use them in our BME 300 level class, which is an undergraduate engineering design method course. It focuses on medical device design and testing. And in that course, we take students all the way from designing models of blood vessels to putting medical devices in those blood vessel models and testing them. So the course begins with tutorials in SolidWorks and other software programs to create idealized blood vessel models in virtual form. We then move on to using mimics for Materialize to create anatomical blood vessel models from real patient data. And the students then simulate flows in those models using the computational tools that are bundled with Flow Coach and HemoFlow. And then finally move on to building physical models, putting real medical devices in them, and then testing the effects that those medical devices have using the Flow Coach and HemoFlow particle image velocimetry platforms. Rapid prototyping plays a critical role in our curriculum, and it interfaces quite well with the Flow Coach and HemoFlow systems because we can reconstruct geometries from any patient data set from CT or MRI or even angio. And using those data, we can then rapid prototype a blood vessel model, recast transparent material around that, and then plug that material directly into our Flow Coach system. The exciting thing about that for our students is that they're able to go all the way from medical image data to doing a medical device test using a real patient geometry. So rapid prototyping gives us the vehicle that we need to get from patient data that's reconstructed in virtual form to a physical model that we can put into the HemoFlow and Flow Coach systems to then be used with real medical devices. The response to HemoFlow and Flow Coach has been amazing. The students, first of all, they really enjoy getting to do something that's hands-on. Many medical device curricula will involve components of design and hypothetical design scenarios. But because the students have these systems in our courses, they're able to take real medical devices, they're able to put them into models of blood vessels that have come from real patients, and then they're able to test firsthand and really measure how fluid dynamics have changed as a result of treating the blood vessel. That experience for them has been invaluable because they're not just doing math on paper, and they're not just designing hypothetical devices to treat a patient. They're getting to work with the real thing and do a real hands-on start to finish exercise in designing a device, validating it, and verifying that it works. I would absolutely recommend the HemoFlow and Flow Coach systems to other institutions. Again, the response we've had here from using the systems has been outstanding. And for any other educators who view this video, I'd also be happy to share any of the curriculum materials we've developed here to facilitate using Flow Coach and HemoFlow in new courses that they might be interested in developing.
And as you heard, our users freely share their curriculums. University of Iowa, for example, they even put it on our website. So we can make it available to other users. Now, we're committed to providing robust quality products that respond adequately to the requirements of our customers. All these are made using state-of-the-art CNC equipment. enabling the highest quality precision machine parts. And our systems are actually designed with student in mind, so they're pretty robust. Our team includes engineers, consultants, including doctors, biomedical engineers, software, mechanical, electronics engineers. We specialize in developing products to be used in labs and classroom education. Very important note, we also establish partnerships with universities. In particular, we work with professors very closely to develop testable new ideas to implement them into our new products. And we definitely regularly publish joint papers, and we encourage that a lot. So finally, our competitive advantage is we offer unique design solution for your educational needs. We have won several Phase 1, Phase 2 SBIR awards, and these are several $1 million, very highly competitive to develop our products. And to be able to win this, it means a lot to us, of course, because it's given by the National Science Foundation here in the US, a very prestigious institution that funds promising and great ideas like ours. And our products are patented as well. So if you have any questions, please don't hesitate to contact TESCON or Interactive Flow Studies anytime. Don't hesitate to email me as well. Thank you very much.
Thank you, Dr. Murad. We have a few questions. First, what is the velocity range for the operation of mini PIV?
We never tested the extremes, but I personally have done up to 5 meters per second. The area is important also because of the seed density and the laser power. So it depends which system you use. If you use 1 megapixel, or 4 megapixel, or 200 milliwatt laser, or LED, or the 1000 milliwatts. So it depends what combination you use. So we're talking about less than a foot square, around 5 meters per second, or maybe more, maybe. As the resolution got higher now, it's maybe be able to measure higher speeds.
Okay, there's another question. With using LED volume illumination, can we perform volumetric PIV measurements?
Well, volumetric flow measurements it requires different algorithms that our software doesn't do yet. Volumetric LED, what we do is we utilize the laser sheet, the camera focal plane thickness as the plane of measurement. And our software takes care of the background or foreground noise, if there is any. And the results are pretty good. So it is not a volumetric flow. You need, I think, 3 cameras and very, very fast pulse rates for that.
Okay, there's another question. Could you briefly explain the mini LDV system?
Mini LDV system is basically, LDV is laser. It stands for laser Doppler velocimetry. So you have 2 beams that intersect, and at the intersection, you have this little volume, in terms of micrometers or millimeters, depending on where they intersect, and you get these fringes, and as the particle flies through those fringes, it scatters light, and the frequency that is received is a function of the speed of the flow, if that makes sense. It's a point measurement. So you have to move the LDV. So it always comes with a traverse. So it has to traverse the flow field. You take hundreds of measurements at one point, and you move to the next point, hundreds of measurements, and you take an average of that. So that one point gives you one velocity vector. And then you move it to the next point. So you need a traverse. It comes with a traverse. So you have to traverse the flow field. It's not a global measurement. The only instantaneous velocity field is obtained with PIV. LDV is a point measurement. Does that help?
Yeah. So there's a last question. Would it be helpful microfluidics for flow visualization micro devices?
Microfluidics is a completely different animal altogether because it requires fluorescent particles and so on, and a microscope or a microscopic lens. We never got into that. Well, or shouldn't say never will, but we haven't got into that yet. Our next product development is actually in renewable energy. So we're developing a product in renewable energy at the moment. So our focus is on software development with our current systems and developing new products in that field. But microfluidics, yeah, I know a lot about it. I've done a lot of micro PIV measurements with other systems, but we haven't actually developed that.
Okay, one more question. What is the exact meaning of mini in mini PIV and mini LDV?
Well, mini mini is just less powerful than the industrial grade lasers. For example, a real industrial PIV system, utilizes YAG lasers, which will blind you, and is like $50,000, $100,000 just the laser. Very expensive cameras and so on. So those are industrial grade laser systems, LDV systems, or PI systems. The mini component, means it has less power, smaller areas, lower velocities, but for educational or basic research is more than sufficient. It should be giant PIV for education. The mini PIV is really referring to differentiate it from industrial, lasers or industrial grade PIV systems and LDV systems.
Okay,
Okay,
one more
one more
final.
final.
How do you
How do you
obtain
obtain
time
time
clock and time average flow data in case of turbulent flows and boundary layers?
Uh, how you cut out again? Can you repeat that? I heard every other word.
How do you obtain time resolved and time average flow data in case of turbulent flows and boundary layers?
Uh, I'm, I'm still not sure what you mean, but let me explain it. If it's not clear, I'll try again. Okay. So first of all, measuring measurements, using PIV near the boundary layers is really difficult because near the boundary layers you have high shear gradients, and to get particles into that layer is really really hard. That's one problem. So your seed density is really low down there, close to the walls, and you need a good amount of seeding to get good PIV data. Secondly, reflection. So when you shine a laser or an LED onto a surface, it reflects. So right on the boundary, it's quite tricky. Of course, there are, we have another system, measures the shear flow. It's a system that you actually bolt onto a surface from under. So you drill a hole and you bolt it through. And so, that then solves a lot of the problems. So it has challenges, but measuring boundary layers is very challenging in itself. So, I'm not sure how close we can get to the boundary layer with the general systems that we have.
Great.
Great.
Thank you,
Thank you
everyone.
again.
We
We
appreciate you
appreciate
being
you
here.
here.
Please feel to
Please.
contact us if you have any questions later. Thanks again for
Sure.
joining us today, and we will see you next time.
Thank you.